Welcome to The Explainer. Today, we are looking at something absolutely massive. We're unpacking OpenAI's O1 model, and together, we're going to see how it fundamentally rewrites the rules of artificial intelligence. For a long time, we've just been used to AI that instantly spits out responses based on oceans of memorized training data. But O1? It introduces a completely new paradigm. It shifts the entire focus away from just brute force memorization and moves it toward dynamic problem solving and highly structured logic. It's a thrilling new frontier, and we are going to break down exactly how it works under the hood, why it matters, and how developers are actually deploying it in the real world right now. Okay, let's dive into this. What if, instead of reflexive instant answers, an AI actually paused to reflect? This single question is really the beating heart of the O1 model. Think about it. We are so incredibly used to hitting enter on a prompt and just watching the text instantly stream across the screen. But O1 operates completely differently. It creates this monumental shift in AI problem solving by taking time, sometimes just a few seconds, but sometimes full minutes, to generate a hidden chain of thought before it ever speaks to you. It's simulating different strategies in the background, it's checking its own work, and it's figuring out the best path forward, honestly, very much like a human expert would when they're faced with a really tough problem. So here is our cognitive roadmap for this explainer. First up, the inference scaling paradigm. Second, smarter, safer, but slower. Third, the science of reasoning. Fourth, verifying the thoughts. And finally, number 5, smart deployment strategies. Let's jump right in. Section 1, the inference scaling paradigm, shifting from training to test time compute. So recently, a lot of experts thought AI capabilities were kind of hitting a plateau, They were predicting that just blindly feeding more and more data into these giant training runs was starting to yield diminishing returns. But, well, here is the breakthrough: test time compute. Basically, this means the model dynamically enhances its own performance by generating longer, detailed chains of reasoning during the actual inference phase, which is the moment it's answering your specific prompt. Think back for a second to how the AI system AlphaGo defeated human champions at the board game Go. It didn't just rely on its pre-training, it used real-time search during the actual gameplay to simulate different strategies, extending its capabilities way beyond human limits. OpenAI's O1 is taking that exact same philosophy and bringing it directly to large language models. What's really interesting about this slide is how it frames the shift. Think of the old way, a training time focus, as basically cramming a giant encyclopedia into your brain right before a big test. It relies on massive, heavy models just to memorize facts. But the new way, an inference time focus, is more like having a lean, incredibly sharp problem-solving engine. By entirely decoupling the reasoning part from the raw knowledge part, the AI can dynamically solve really complex problems without needing to literally be a massive encyclopedia. It essentially shifts all the heavy lifting to the exact moment you ask the question. Section 2, smarter, safer, but slower, the new performance benchmarks. Okay, prepare for a massive wow factor here. We are looking at the AME math competition, which is an incredibly rigorous test. Notice the stark contrast, this massive jump from a tiny 12% bar for GPT-4o all the way up to a staggering 74% with O1 Preview, and that's on its very first try. And it gets crazier. When it's allowed to use advanced techniques like consensus re-ranking, which is basically the AI double-checking its own work multiple times before answering, it hits 93%. It is literally outperforming top human PhD experts in complex STEM and mathematical tasks, which, yeah, is mildly terrifying, but just absolutely incredible. But it is not just math. Look at this number, 84. This is a one preview score out of 100 on the highly difficult strong reject safety benchmark. Now, to put that into perspective, GPT-4o scored a 22 on this exact same test, 22 to 84. This massive leap happens because the model now reasons through safety rules in real time. Instead of just bouncing off rigid, pre-programmed guardrails, O1 actively thinks about the implications of your prompt. It can logically determine if a request is trying to trick it into violating safety rules. For the everyday user, this matters immensely because it drastically reduces the system's vulnerability to jailbreaks, making AI products way safer and more reliable for the general public. Right, let's balance the hype with reality for a minute, though. O1 is a brilliant thinker, sure, but it would actually be a pretty terrible pub trivia partner right now. It has very limited non-STEM trivia knowledge. Honestly, if you want literature trivia, an older model is going to be much better. O1 is also slower, and it is significantly more expensive because all of those internal reasoning tokens it generates to think, well, they're hidden from you, but you are absolutely still billed for them. Plus, right now, it lacks support for external tools or image inputs. So keep in mind, it is a highly specialized reasoning engine. It's not a broad, multimodal, do-everything tool just yet. Moving on to Section 3, the science of reasoning, inside the academic breakthroughs. So the crucial point is, how is this massive data flywheel of thought actually achieved? How does a model learn to think in the first place? Well, this brings us to a framework known as the STR method, which stands for self-taught reasoner. First, the model produces reasoning chains. If they lead to the correct answer, great, it keeps them. Second, it fine-tunes itself on those successful chains. But the third step, this is where the magic really happens, is rationalization. If the model fails a problem, it's given the correct answer and forced to work backward to figure out the right rationale. It is literally, iteratively bootstrapping its own logic and teaching itself how to reason. This foundational research eventually led to the Quiet Star paper, which proves a truly fascinating point. Language models can teach themselves to think before speaking. The researchers discovered that by forcing the model to generate continuous hidden thoughts, or rationales, at every single token position, it drastically improved the model's ability to reason out of the blue, even on tasks it wasn't specifically trained for. The model essentially learns that stopping to take a breath and think is highly rewarded. Section 4, verifying the thoughts, grading the process, not just the outcome. So if the AI is generating, minutes of internal thoughts, how do we actually know if it's on the right track during all that long inference time? This brilliantly illustrates a shift in methodology. Instead of outcome supervision, where you only grade the final answer at the very end, we use process supervision. This means the system grades every single intermediate step in the AI's reasoning chain. Think of it like a math teacher giving you partial credit for showing your work, step by step. These process reward models, or PRMs, guide the AI along the way, and they proved vastly superior for training models on super complex math and logic. And to make this even more bulletproof, researchers developed the V-STAR framework. Actually, instead of only learning from the correct answers, V-STAR iteratively trains verifiers using both correct and incorrect solutions. By explicitly showing the model its own mistakes, rewarding good logic and heavily penalizing bad logic, its reasoning becomes incredibly sharp. It essentially learns exactly what a bad thought process looks like, so we can steer clear of it in the future. Finally, Section 5, Smart Deployment Strategies, making inference-time compute affordable. Now, let's transition from the cool academic theory to cold, hard, practical reality. Deeper reasoning means more compute, and more compute means much higher costs. So it's the multi-million-dollar question. How do we actually afford this deeper reasoning? I mean, if every single basic user prompt triggers minutes of deep, expensive test-time compute, developers would go bankrupt overnight. We absolutely need dynamic task routing to ensure we only pull out the heavy artillery when it's absolutely necessary. One highly effective solution to this problem is the dual net approach. You basically employ a smaller, much cheaper side net to run alongside the powerful main net, which is your O1 model. The side net acts as a preliminary filter. It quickly assesses the complexity of the prompt and its own confidence level. If you're just asking for help with a routine coding syntax error, the side net handles it instantly and cheaply. But if the task is a complex, multi-step STEM problem, only then does the system invoke the expensive main net. Let's move to and see how this builds directly into intelligent architectures like Route LLM. It evaluates query complexity dynamically on the fly, routing the simpler tasks to the cheaper, faster O1 mini model, and reserving O1 preview exclusively for the heavy lifting. For any developers watching, this is huge. It means you can see up to 2x cost savings without sacrificing any response quality. It's the perfect way to balance budgets while still leveraging world-class reasoning. So we've seen how test-time compute is entirely decoupling knowledge from reasoning, allowing these models to pause, reflect, and verify everything step by step to actually outperform human experts in complex tasks. But all of this leaves us with a really profound thought to ponder. As AI officially transitions from reflexive answering to reflective reasoning, what complex problems will we ask it to think about next? The paradigm has officially shifted, and the real-world applications are just beginning. Thank you so much for joining me for this explainer, and keep learning.